is separation of a dye mixture using chromatography. Using a clean toothpick, spot the chromatography strip by placing a toothpick into the dye mixture and then touching the tip of the toothpick gently to the designated pencil dot. Watch carefully as the solvent makes the dye go up. So why does the dye go up?
As to what determines the attraction, polar attracts polar, so the most polar solvent, 2% isopropyl alcohol, attracts best to the most polar dye.
The overall purpose is to basically separate substances into mixtures to investigate the factors that influence separation, such as polarity and intermolecular forces.
In real life, chromatography is used primarily for forensic sciences.
Okay, so today we are going to be making a hand warmer out of a calorimeter using an ionic compound and 2 styrofoam cups inside of each other.
We have to make sure that the calorimeter works as intended and doesn't lose too much heat. The way we do this is by adding 100 milliliters of room temperature water and then adding in 100 milliliters of anywhere from 60 to 70 degrees Celsius water, and after 20 seconds, measuring the temperature of that.
First experiment, you're going to do 6 more of those each with all these compounds with starting magnesium sulfate, calcium chloride, sodium acetate, ammonium chloride, sodium carbonate, sodium chloride, and the one we just did was lithium chloride. So after we measured all 7 of our compounds in the water, we found out that lithium chloride had the highest change in temperature.
But the reason that lithium chloride stands above the rest is because if you look at a periodic table, lithium is thusly the electrons in the lithium chloride compound are so closely attracted to the nucleus that it requires a large amount of energy to break them apart, which is what's happening when you add it to water. All ionic compounds break down in water, but lithium chloride out of these 7 requires the highest energy, leading to the highest increase in temperature.
Today we will be doing a redox reaction with titrations to see the percent composition of hydrogen peroxide in household products.
First, what you need to do is take some deionized water or distilled water.
Add 10 milliliters of sulfuric acid into the flask. Now measure 10 milliliters of hydrogen peroxide and add it to the flask. Record this volume in an appropriate data table. We will now fill the burette with potassium permanganate very carefully using a funnel. It can go anywhere between 0 and 10 milliliters, but make sure to record the volume of where it is filled to. We will now titrate the hydrogen peroxide with potassium permanganate. Make sure to record the final volume of potassium permanganate left in the burette when you are finished with the experiment. The following is an example of the pink color that persists when you are finished with the titration. We will now find the percent of hydrogen peroxide. We will do this by dividing the mass of hydrogen peroxide found in the previous problem by the mass solution and multiplying the whole quotient by 100. So our mass of hydrogen peroxide was 0.0279 grams, and we will divide it by 1 gram and multiply it by 100, and we got 2.79% of hydrogen peroxide.
In the end, our average percentage from both trials was about 2.84%, which is a bit of a stretch from the expected 3%. Remember, the purpose of this experiment was to find the percent composition of hydrogen peroxide in various products.